Yeah, so then we just continue homework 5. So problem 9 of homework 2, if there is a placebo effect or not, so state the null and alternative. Okay, so yeah, so our alternative, null and alternative will be, or the null will be d bar for the placebo equal to 0, and d bar not equal to 0, where d is referring to the, or first, I think from the homework 2, there's 5 numbers for the placebo effects, and before placebo and then after placebo. So we have 5 number for that and another 5 number for the after. And the d is referring to the difference, where we use a placebo after these 5 number minus these 5 numbers element wise, and we'll have another a vector of 5 numbers, which we represent as the difference, or d in here. And then the d bar is just the average of the 5 number that we just calculated. So with the new data, with the new 5 numbers that we could just construct, we then calculate the estimated standard error, which is the standard deviation of the 5 number here, and then divided by square root of 5, which is the sample size. So once we have that, we can then proceed to calculate this test statistic, which is the mean of difference, which is denoted by d bar, and then minus 0. 0 is come from here. We are trying to or evaluate or to test this hypothesis, which is equal to 0. So we minus a 0, and then divided by the estimated standard error, the one that we just calculated here. And that will be our test statistic. And then to calculate the p-value, we just using this is we only have 5 data points, so a relatively small data set. So we use the t-distribution for this test statistic, degree of freedom 5 minus 1. And also we have alternative is not equal to 0, so we have this is a 2-sided test. So don't forget to multiply by 2. And then this will be our p-value for this hypothesis testing. And because it's greater than 0.05, we do not reject the null. And then just, yeah, for most of the question, you can also verify the answer on your own. So here it's just a built-in function in R that you can just like a one line, and then you can just directly run everything what we did here. And it returned the same p-value here. So it basically just kind of verify the formula or the idea or the things that you did here is correct. And then it generates the same p-values and same conclusion. So any question or comments? Okay, so yeah, question 2. 4 number, normal distribution, another 5 numbers, and same variance, same normal distribution. So do you think the mean for the both normal distribution are the same or not? Formulate a hypothesis testing problem, and well, calculate a test statistic and the p-value. So 4 number and another 5 numbers. And we have the equal variance assumption, so we need to use the formula for the pool variance. So here what I did is just plug in the formula and then calculating the estimated standard error based on the equal variance assumption. And then after we have that, we can just calculate our test statistic. So we use the mean of x minus mu of mean of y. And also here there's a minus 0 because this is referring to our null hypothesis. And then divided by the estimated standard error. And then will give us the test statistic. And again, this is under the t-distribution, test statistic, and the degree of freedom is 4 plus 5 minus 2. And don't forget multiply by 2 for the not equal or two-sided test. And then you should be able to calculate the p-value 0.11. And greater than 0.05, so do not reject. And then again, just to verify the answer by directly calling this t-test, we also get the same result. So basically this function, built-in function, did what we do it, everything here manually. And yeah, it returned the same p-value, and then it will give you the same conclusion. Yeah.
Are we expected to like write out the equations, or we can just code it in R and then just do a number?
I'm not sure if you are allowed to do that in because in previous year, I think the professor explicitly asked you to show this. No, I mean you have to write it down like as a formula to plug in the number, not just the code. Is that your question?
Yeah. Okay.
Yeah, maybe. Yeah, have to write down the formula, not the code, formula, and then use calculator or something to plug in to calculate that. So not only the code and not even this built-in function directly. Yeah, but what I'm showing here is just for you that you can verify to tell you that you get the correct answer by doing manually by hand or call the built-in function. You should get the same result. And this is what we show here. So 0.117. Yeah. But very likely during the exam, probably you will be asked to write down the formula. I mean, on paper and then plug in the number. Yeah. Any other question? Okay. Question 3. So, coin tossing. This amount and then proportion of landing on head. We are trying to test that h now is equal to 0.5, and then a two-sided test. So alternative should be not equal to 0.5. Find the p-value, state the null and alternative, and based on the alpha level, give a conclusion. Yeah, okay, so here is the null and alternative, equal to 0.5 and not equal to 0.5. This is the one that we observed, so this will be the proportion of landing on head out of that many tosses. And then the estimated standard error is based on the binomial distribution. So we have this p multiplied by 1 minus p over n. And take the square root, we have the estimated standard error. And then here, our test statistic is the observed p hat minus 0.5, which inherit from the null hypothesis, over the estimated standard error. Then we construct our test statistic, and then this one under the normal distribution, and test statistic lower tail equal to false. So this is probably is going to be some positive value. So we let the lower tails equal to false, and it's a two-sided test. So don't forget to multiply by 2, and then we have the p-value here. Less than 0.05, so we reject the null that is equal to 0.5. Any question? Then for question 4, so this time just 5 coins at a time. And this is the frequency. So 100 times that all 5 coins lands on tail, so 0 heads. And then this amount or occurrence for only 1 out of the 5 coins landing on heads. And then the frequency for each of the possible sample or the outcomes. So test if the data are consistent with the hypothesis. And that all coins were fair coins. So all of them should be 0.5. Pearson chi-square test report a p-value conclusion. Okay, so our null hypothesis is going to be like this. So under the binomial distribution, we have 5 coins, and then the probability that landing on heads is equal to k for k range from 0 to 5. So this will be our null hypothesis. And here we just create a vector for all the 6 outcomes, and then a placeholder, and then the total occurrence. And then in the for loop, for ranging from 0 to 5 or 1 to 6, here just do, since it's 1 to 6, so here just do I minus 1 to get the count, as the actual outcome is from 0 to 5. And the expected value is that n multiplied by p, and then the probability is referring to this binomial distribution, the one that we have here, and then for each of the k ranging from 0 to 5. So within this for loop, for each of the from 0 to 5, we calculate the probability. Multiplied by n, it will give us the expected count. So this is the one that we observe, the counts that we observe, and this is the expected count that we're going to calculate. And finally, the ratio corresponding for each of the outcomes is equal to observe for that outcome minus the expected for the outcome, square over the expected for the outcome. So we'll then report, we will have a 6 number in the ratio. And the last step is to use the chi-square distribution, and the test statistic will be the sum of the ratio, degree of freedom 6 minus 1, and then lower tail equal to false. That will give us the p-value here, less than 0.05, so we reject the null. Any question or? Okay, then for part B. So test to see if the data are consistent with the hypothesis. They have the same probability, but not necessarily 0.5. So part A is asking that all of them equal to 0.5, and part B is saying that it can be any arbitrary value, P, for each coin. And then do the same thing, but yeah, in this case, we need to estimate the P instead of just directly using 0.5. So just to show the difference, here we use 0.5 directly in our null hypothesis. But in this case, here we don't know the P. So in this case, we need to estimate this particular or additional variables or unknown, or a piece of unknown information in this null hypothesis. So in this case, we are going to use MLE to estimate that, and then under the binomial distribution from the observed data, we can estimate the PMLE for this set for this observation, and that P will represent. We'll use that P as this value here in our null hypothesis. So here we calculate the P based on this data set instead of 0.5. And then we repeat the same thing. And just to make sure that this P here is no longer 0.5, it should be the one that we calculate from our original data set. That's the difference. And then the last difference is that right now the degree of freedom, instead of 6 minus 1, we have 6 minus 1 minus 1. The additional minus 1 is because we use the data to estimate another unknown information in this null hypothesis, which is this MLE for this binomial distribution. So we need to minus 1 for additional degree of loss in the degree of freedom. And rest of the template stay the same, and calculate the P value. 0.06, so greater than 0.05, we do not reject the null. So in this case, when equal to 0.5, it seems like we reject the null. And once we have this additional information, we do not reject the null. But it may not necessarily be 0.5 anymore. Yeah, but our conclusion is that we do not reject the null. Yeah.
How did you get the formula for MLE of P?
You can take the joint and then the same procedure. Yeah. Yeah. Any other question? Okay. Question 5. So 4 different categories, their corresponding probability and the occurrence. Pearson goodness of fit test to see if the data compatible with the null hypothesis. So then our null will be like this, the probability for each of the category and their corresponding probability. So again, we don't know what the theta is, so we are going to estimate the theta by MLE. And this MLE formula here is the one from one of the previous homework question. So this you already derived, so I just directly take the formula here and then calculate that. But this line here is just to calculate the theta MLE based on this particular observed data. So we estimate this theta MLE. And then we just follow the same procedure. Observed data, placeholder for the expected value. And this is the corresponding probability. This is just another way to rewrite 0.25 multiplied by 2 plus theta, where the theta is replaced by the MLE. 1 minus theta, 1 minus theta, and then the theta. Yeah, so another way to rewrite that. And then in the for loop, our expected value is the one unmultiplied by the probability that we just calculated, where the probability is that the theta replaced by the MLE. We have that, calculate the ratio for each of the outcome. And the same procedure here, degree of freedom 4 minus 1, and then a minus 1 for that we use the MLE to estimate this theta. P-value for that, we do not reject the null. Any question? Okay, question 6. So 10 tosses test the hypothesis that p equal to 0.5 versus p not equal to 0.5. And the test reject the null when it's either 0 or 10 heads are observed. So what is the significant level and what is the power when the true probability of head is 0.01? Okay, so this one is referring more the definition for the significant level and power. So the level of significance is probability of rejecting the null when the null is true. So in our case, our null is that p equal to 0.5. And then we also know that the criteria for rejecting the null, which is either 0 or 10. So out of 10 tosses, observing a 0 and a 10 can be calculated by this probability here. So this is the density or the probability for a binomial when n equal to 10 and then k equal to 0. So the probability for observing is 0. And this part is the probability out of 10 tosses observed 10 heads. And these are the two density or the two probability. Once we calculate that, the sum of them will be the probability of rejecting the null. And this is also under that null equal to true, where null is 0.5. So here we use 0.5 to calculate that. And the sum of them will be the level of significance. And then in contrast, the power is referring to reject the null. So the same part, reject the null. And when the alternative is true, and based on the question, the alternative is 0.1. So here we are going to calculate the same probability for out of 10 tosses landing on 0 hats and 10 hats. But this time under that the null or the p is equal to 0.1 instead of 0.5. And then the sum of them will be the power. Any question? So the same sum of the two outcomes, except one is based on the null and the other one is based on the alternative. And then give you the definition or the two, one is the level of significance and the other one is the power. Yeah?
Is the choose function, that one's the combination?
Yes. This is the binomial coefficient. (16) random variable, keyword IID, normal mu, unknown mu, and then variance equal to 4. We are interested in the x bar, which is the sample mean. Test against that this mu is equal to 0 or this mu equal to negative 1. Reject the null when the x bar less than c. Find the value c such that the significant level equal to 0.01. Okay, back to the definition for the significant level. This is the null and the alternative based on the question. The data, each of the x come from this normal, and the x bar follows the normal distribution with the same mu, but the variance is equal to 1/4. And here is the definition for significant level. So rejecting the null, and when the null is true. So when the null is true is that we condition on mu equal to 0. So when the null is true. And this part is the rejection criteria based on the question, x bar less than c. So we first need to find the value of c. And we also know that this x bar follow a normal distribution. So yeah, we just need to find the quantile for c such that the area under the curve up to this c has the probability 0.01. So just find the quantile for 0.01 and under the distribution for x bar. So mean 0, which is the null hypothesis. And then the standard deviation square root of 104 has come from here. And then we find the quantile is that negative 1.6. So now we have the value for c. And yeah, so that is part A. Just find the quantile that satisfy the definition for the level of significance. Then for part B, based on the value c, find the power of test. So now refer to the definition for power. Again, rejecting the null when the alternative is true, where the alternative is that mu equal to negative 1. So now we just calculate the p norm, the probability that up to this quantile here, and then calculate that probability under this normal distribution. So mean is equal to negative 1 and same standard deviation. And we found that the power is this one, is this, yeah. If it's asked for beta, then you need to do 1 minus that. But yeah, this one should directly output the power. Yeah. So both of these questions are just referring to the definition. So the significant level is rejecting the null when null is true, and the power is that rejecting the null when the alternative is true. Any question? question 8. Okay. So unmeasurement under treatment and another unmeasurement in control, independent, and then a single observation is normal. It seems like unknown mean and standard deviation 10. How large n should be for the test for this null and alternative has a power equal to 0.5? And also when the alternative is 2 or has a power and the alpha level set to 0.1. So yeah, the question is that trying to find the number of n based on this setting here. So we first construct or to write down all the information we have. So x follow that with mu x and y follow normal with mu y. And then we are interested in the difference of their mean. So x bar minus y bar will follow a normal distribution in this form. So mu y minus mu y, mu x minus mu y, and then 2 sigma square over n, so 200 over n. So this is our the distribution that we're going to work with, and then we have the null and alternative equal to 0, greater than 0. Okay, so we will reject the null when it's greater than some value c. And under this condition for the significant level. So when the null is true, and so this is just rewrite the significant level. And now we're trying to calculate or to simplify this form. So we know that x bar minus y bar follow this. Under the true hypothesis, or under the null hypothesis, this part is equal to 0. So we have x bar minus y bar minus 0 here, and then over square root of the standard deviation. We apply the same procedure on the right-hand side. So c minus 0 over that, and then we have the left-hand side standard normal greater than this particular value equal to 0.1, where here when we have that when we are trying when we want to set the alpha equal to 0.1, and then we have this relation. So this is the quantile such that under the standard normal distribution we have I think there should be 0.9 under the area under the curve because we have a greater than this sign here. So we have this equation here as one piece of information for now. And then we want to start from the other, which is the power. So the same rejection criteria, but under the alternative hypothesis, also given by the question when the difference is equal to 2. So now we have this x bar minus y bar minus 2 under the alternative instead of minus 0. Same procedure on the right-hand side. And then c minus 2 over the same standard deviation. And this is equal to 1 minus beta. And then, let's see, power equal to 0.5. So based on that condition, that is equal to 0.5. And then we have another equation here. So the probability under normal up to, to give you the probability equal to 0.5 has a quantile of 0. So that we know that this part is going to be a 0. So we have two equations here. So one is that come from the level of significance, and another equation come from the power. And now we are trying to solve for the only unknown n. So based on this, we know that c is equal to 2 by c minus 2 equal to 0. So c equal to 2. Once we obtain that, we plug the c into this equation here. So 2 over the square root of standard or the variance equal to that, and then we can just directly calculate the n, which is 83. So we start from the definition of level of significance, and then we have one equation here. then from the power, or the definition of power, we have another equation. So two equation, two unknown, and then the n is the one that the question is asking for. And then we can calculate the value for that. Any question? Okay. Then true or false. So significant level of a test equal to the probability that the null is true. So yeah, so this is false. We just go through again and again for this. So we just reject the null when the null is true. That is the meaning for, or the definition for the significant level. There's no such thing called a probability that a statement is true. Your statement is either 0% or 100%. There's no this probability that something of a statement. So yeah, and also that doesn't align with our definition for the significant level. And if the significant level of a test decrease, the power increase. For this one, it would be better to refer to the graph for significant and the power. So if you look at that graph, you will see that it is not the case when or you can just refer to any graph that has the both significant level and power, and you can see how you shift the line, and you can see that they do not always move in the opposite direction. So yeah, and then so this is going to be a false. But it will be easier to see from that graph. And then once you shift the line, and then you will see that the significant level and the power can also increase at the same time.
Do we need to justify our answer?
Let's see, true or false. So you probably know. Yeah, you don't. Yeah. Reject the null at the significant level 0.1, and that means there's 99% the probability that null hypothesis is false. So again, so that or maybe I don't know how to justify this. It just, to me, there's nothing that a statement is false has a probability. So you either be true or false, 100% or 0%. So there's no this kind of a conclusion, and that is also not the explanation for rejecting the null. So similar to A, which is also wrong or false. Then for part D, the probability that the null is correctly rejected. So here the probability is talking about rejection, not just not about the statement, and then it's equal to the power of the test. So that is true, which is what we just talked about, or the definition for that. And then if the power of the test is 0.8 and that is equal to 0.0, then that is equal to 0.2. So again, if you refer to a graph that contains both significant level and the power, you will also see that they does not necessarily sum up to 1. So yeah, so that is just not when one is alpha, the other one just 1 minus alpha. It's not the case. So that is also a false. And then for 10A, so the p-value is 0.03, and the null is to reject at 0.1. This should be false, because what we did is that when the p-value is less than the alpha, then we reject. But this here is greater than, so we should not reject the null. Then for part B, so if we reject the null at significant level 0.1, the p-value is less than or equal to 0.1. And that is true, and that is what we did in this homework. So when p-value less than alpha, we reject the null. And for part C, so p-value 0.001, and that is the probability that this is true. So again, this is not, there's no, yeah, it just, to me, it doesn't make sense. So, and then it's also a false. And then for part D, for chi-square test, degree of freedom 4, test statistic 8.5, the null hypothesis is rejected at alpha level 0.05. So here we just do the same thing based on the information here. We can see that the p-value is actually 0.07, which is greater than 0.05. So we do not reject the null, which means that this is going to be a false. And then the last one, so p-value 0.02, power 0.98. So again, there's some, does not necessarily sum up to 1. And which is going to be false. And yeah, that concludes our homework 5. Let me stop the recording.